Look at the towering sand dunes of the Namib Desert, or the jagged, snow-capped peaks of the Himalayas. Earth's surface is in constant motion, shaped and reshaped every single day. Now, compare that to Mars. The Curiosity rover has spent over a decade rolling across a cracked, crater-pocked landscape that has remained effectively frozen in time for billions of years. Why does our planet constantly renew itself, while neighboring worlds sit stagnant? The answer lies in thermodynamics. Earth operates on two distinct heat engines, the external solar engine of the sun and an internal engine deep within the planet's core. The external engine is easy to see. Solar radiation heats the atmosphere and oceans, driving the weather patterns, wind, and water currents that slowly grind down the surface. But the internal engine does the heavy lifting. Hidden deep beneath the crust, it generates the immense force required to shove continents across the globe and thrust up massive mountain ranges. Earth operates as a massive, complex thermodynamic machine. Its active, moving parts constantly fight against the planet becoming a dead, silent rock. To understand how those moving parts operate, we have to strip away the crust and look at the fuel source. Earth's core burns at nearly 10,000 degrees Fahrenheit. That intense heat is a combination of leftover kinetic energy from the violent collisions that originally formed the planet and the slow, steady decay of radioactive isotopes trapped deep inside. As that heat radiates outward, it bakes the thick layer of rock above it, the mantle. Over millions of years, these extreme temperatures soften the solid rock, making it pliable. This creates a layer called the asthenosphere. Here, the ductile rock is caught in a continuous loop of motion known as mantle convection. The glowing core heats the rock directly above it. That warmer, less dense rock becomes buoyant, slowly flowing upward toward the crust. Once near the surface, the rock cools and becomes denser, sinking all the way back down to the core. This process transfers massive amounts of thermal energy, but it happens at a glacial pace. We are talking about the creeping flow of solid rock, not boiling liquid water. This endless rising and sinking inside the mantle translates the planet's raw internal heat into sheer mechanical force. For a long time, geologists assumed the crust was just floating cargo, that continents were pushed around entirely by these convection currents, like tea leaves floating on a simmering pot of water. We now know the rigid tectonic plates are part of the engine itself. They are driven largely by their own gravity. Plates form at mid-ocean ridges, where hot magma wells up and hardens. As this new rock travels outward away from the heat source, it cools and becomes incredibly heavy. This diagram illustrates what happens at subduction zones. The dense, cold edge of a plate sinks into the mantle. As that heavy edge drops deep into the earth, gravity takes over and drags the entire plate behind it, a mechanism called slab pull. Plate motion is a massive push-pull system. You have mantle convection pushing hot rock up from below, and gravity pulling cold slabs down from the edges. When millions of square miles of dense rocks separate or slam into each other, the physical exhaust is visible on the surface. Where these plates grind together, intense friction and heat melt pre-existing rock into magma. That liquid rock bursts back onto the crust, creating thousands of active volcanoes. The mechanical pressure of continents colliding forces solid ground to buckle. Over time, flat plains are thrust miles into the sky, forging mountain ranges like the Zagros in Iran. This continuous cycle of creation and destruction forms the bridge between Earth's two great engines, creating what we call the rock cycle. The internal engine relentlessly builds new landforms and pushes them upward. The external solar engine immediately starts grinding those landforms down, washing the sediment into the oceans to eventually be subducted back into the mantle. Without that internal tectonic cycle replacing what the sun and rain erode away, solar erosion would eventually grind all land masses flat. The chemical nutrients required to support biology would end up trapped at the bottom of a stagnant ocean. Plate tectonics provides the mechanical rhythm that continuously cycles carbon, water, and minerals. It is the planetary heartbeat that keeps our world dynamic and hospitable.